Mic check. Mic check, camera check. Mic check 01. Coming back in with a little bit more COMP1511. So, eventually, when you're where you want to be, programming proficiently, and when you get your fancy job in your tech company, I want you to give a shout out to your old MC. That's me, MC, MC. What's up, y'all? How we doing? I hope everyone had... Well, you know, I can't say I hope everyone had a relaxing time off in Flex Week, because I know that I myself am part of the memes that everyone was sending around about having an apparent Flex Week but then having to do all this extra work because of assignments. So rather than hoping that you had nice time off in your Flex Week, I'm hoping that you learned something important out of assignment 1 instead. If it makes you feel any better, I also was absolutely bombarded during Flex Week because everyone was like, oh, you've got time off, don't you? And it's like, well, you know, like I'm still doing my same lecture content. And so I ended up doing a whole bunch of extra stuff last week as well. So maybe I'm as tired as you are now, and we're all in it together. William learnt that you shouldn't procrastinate, which is pretty funny. Yeah, so a lot of people had a lot of work to do, but hopefully, I don't know if anyone was around for the Friday lecture that I gave during Flex Week. If you weren't, it might be worth going and checking that out, because that one is all about... It's all more about you than it is about the course, and it's all about thinking about how you want to approach kind of your future, whether it's in programming or not. It talks about professionalism in general, which is just a compiled list of ideas, in a sense, from a lot of people who are working in the tech industry and hiring people in the tech industry, and stuff that I've learned over time watching students get into the industry, and how the kind of skills that it's much harder to teach, but it's kind of important to think about. So could be worth checking out, especially if you're having a lot of trouble with what you're doing. I think there's some nice words in there for people. David learnt that accidentally swapping the dimensions of an array leads to chaos. Yes, it does. There's a reason why we're really, really careful to say rows then columns, and then to like really lay it out. We just go, nah, rows then columns. I'm gonna do it in this really specific way, because if we start flicking it around or being even mildly unclear about where that's going, we get a lot of problems. Okay, let's launch into what we're talking about today. What did we cover last time? So this was 2 weeks ago, so hopefully you do remember this. Don't worry if this is starting to fade from your memory, because it was 2 weeks ago. We will be doing this in the tutorials and labs this week, so we're going to be covering characters and strings and command line arguments. Having said that, I feel like characters and strings, a lot of it is more intuitive than some of the other stuff we've done, because it's about words, and us as humans are much more likely to be, understanding of words and how they work than we are going to necessarily be of numbers. It's a mildly more natural thing for us to do. There's a few things that we want to remember when we're doing this. So we're starting to think about not using all of an array, and so we've got our null terminator, and also we're starting to, rather than just having stuff like scanf and printf, we now have a much bigger set of library functions that we can use. So we're going to be going through all of that in the tutes and labs, and you'll figure a bit more of that out, and slowly, I guess, come to grips with using more code that's not your own. We also had command line arguments. They can be a little bit confusing the first time you use them, especially because they're an array of strings, so it can get a little bit messy, but with a bit of practice, they're not too hard. Dan learned that the assignment is way harder than you think. I think if it, hopefully, it won't happen for everyone in exactly the same way, but hopefully everyone, as you get through the assignment, you hit a point where it's really hard, um, because it's designed to push everyone to a certain point where they get to a certain point and they go, oh, okay, this is where the hard stuff is. So the idea that everyone can complete the assignment and everyone can get 100% in the assignment is not entirely necessary. I think that if you're getting a passing mark in the assignment, or like a what you think is like somewhere around a pass or a credit or something in an assignment, you can roughly, it's not exact, but you can roughly gauge that if you're working at that same consistent level through to the end of the term and in the exam, you'll probably end up with a mark somewhere around that. It's not like, I would never use it to predict someone's marks, because the assignment's only on the first couple of topics and the next assignment's going to be on the next couple of topics, and so they're kind of separate in a sense. But anyway, it's worth thinking about that, like, you know, not everyone's expecting to get 100% in the subject, and in the same way you won't be expecting to get 100% in the assignment itself in general. I know there's like, I don't know, 2 of you out there who are thinking, oh no, I'm going to get 100% in this whole subject. And I was like, okay, cool. I've never I never managed to get anything like that when I was at university. I think I only had 1 or 2 marks in the 90s at all. And Izzy's saying, anyone else didn't get to do stage 4 and 5, ran out of time. Yeah, that's totally fine. So you actually are in that kind of situation, where I was talking about, where you're actually potentially still at a credit distinction level, which is really not that bad. You know, that's actually like decent marks. Like for me, whenever I got a distinction at uni, I was like, okay, that's pretty good. And if I got an HD, I was like, yeah, I really understand that. But, you know, a lot of marks are going to be like passing credit and stuff, and you're like, all right, I've got enough that I can do this if I need to. And if I come back in the future, I know that I got a pass or a credit. It means I could relearn the things that I needed, and I can get this going again. Megats is saying, where do we get resources that could help with the assignment, as it's really hard to find anything remotely related to it? I think, Megats, when we're talking about that, we're thinking about what are the techniques necessary to do the work that's in the assignment. And a lot of that has specifically been covered in what I've been teaching leading up to the assignment, tutes and labs as well. I think going back over our course content is going to be easier than necessarily looking elsewhere for resources. Also, if you want really specific things, if you can't find resources, then the course forums and the help sessions are really good things to do. They got really busy. One of my tutors reported that they were still answering forum questions at 4 a.m. one night, and I said, we really don't want you to do that. We want you to actually get some sleep and things like that. But I mean, some of them were actually still answering your questions right through into the night. So we actually got it down to the point where the forum was getting answers to people within, it was very, very good. Even at peak times, we were still giving answers around like sort of 3 or 4 hours from when they were asked. That was like the longest time period, and so the forums are pretty active. You can get a lot of help there. Okay, so we're talking about characters and strings, command line arguments. Today we're going to look at getting deeper into our memory. So we're going to use 2 things to work with memory. So we're going to do a recap of how functions work in memory, and we're going to get a little bit more detail of exactly what they're doing and why we have that kind of idea of scope, where we know that, and I've told you that variables that are inside functions kind of disappear when the function finishes. Variables that are inside curly brackets also disappear when they finish. But we're going to have a closer look at that, and then we're going to look at maybe we actually want things to last longer than their functions. If we want things to survive past the functions that create them, do we have a way of doing that? And now we do. And in doing so, we can actually get a little bit more little bit more use out of our functions. So we can actually make functions that create things. So we can make a function that creates something, and because we can make it live longer than the time it was in its function, we can then pass objects around in a sense and have them persist. We're going to talk about techniques to do that. Combining that with something we call structs, because the structs are the things that we actually do this with the most when we're kind of programming with the full tool set that you would have by the end of COMP1511. So a struct is a custom variable. A struct is a way that we can actually put together our own data and bundle it up in a variable. So a really, really simple idea is people may have been looking at assignment 1 and thinking about coordinate pairs. So instead of inputting two separate integers into a function every time you want to do a coordinate pair, we could combine those two together and make a variable that has two integers in it. That's what a struct is. We're gonna do more complex things even than that, even today with structs, to show you how you can actually make your own variable types in a sense. So I'm gonna piece those together because they go together a lot, and do a little example today. I again have packed a lot of a lot into the example, so I'm not sure if we'll finish it all today, but we'll see how we go. How are we doing? Oh yeah, everyone's saying that people had to choose when to finish the assignment, like at what stage to stop, and I think that's okay. I think that's the way it goes. I actually did talk about that on Friday as well, if you're keen to look at it. There's a lot of thinking about, we can't do everything, you know, like we want to do everything we can in the world, but we can't always do everything, and so we have to work within our limitations, and we have to stop when it's not healthy to continue, and it's okay to do that. Again, I want to say, not expecting very many people at all to get 100% in the assignment, and it's not really intended for that. It's intended to be this ramping difficulty scale, and you hit a point, you go, okay, this is where I stop, and that's fine. Yeah. Okay. Yeah, as Sean's saying there, if it's 4 a.m. then you should stop. Okay, so let's go back through functions in memory. I've taught this exact thing previously, but all the slides are actually different, so I wrote it twice, so I'm delivering it slightly differently each time, hoping that you will, if you didn't pick it up the first time, then now when you hear it, it won't just be a repetition, it'll be slightly different. So hopefully this works. So everything gets passed into a function by value, what we say. So the function, when it gets input variables, never gets access to those particular variables, but will get a copy of the variables that it's given. So when you start a function, it will create its own variables. So for example, this is the example that's very similar to one that I gave before. So if I have a variable 5, and I use this function called doubler, and doubler takes in a number and then multiplies it by 2. This number here is not the variable x, it is the value 5 that was in the variable x, but it gets created as a new number here as the number 5. It doubles the number, so number is equal to 10, but number only exists between these curly brackets, and when you print this out, x is still 5, right? So this is thinking about the fact that when we pass the variable to a function, it goes in by its value, not by its variable itself. If we wanted to give access to that variable to the function, then it would be considered to be passing in by reference. So passing in by reference to that variable. One of the confusing things as we go on in the future into programming with multiple languages, different languages do this in different ways. So some languages will say everything that you pass into a function is actually access to a variable. C is careful to be able to do it both ways. So we can do it this way and say the only thing that goes in is a value. And it looks, actually no, I went ahead too early. And so the only thing that you get is the number, not the variable itself. If we want to give access to a variable, though, we can use pointers. And so we've learned at least a little bit about pointers. So I've got a pointer in my program, and then I call a function, and the function has its own memory, which is why the function's contained in its own little box here. It will make a copy of the pointer if it was given the pointer as one of its input variables, or one of its input parameters. There's lots of different words for it, so when there's lots of different words or something, I just try to say all the words. If we have the copy of the pointer, it means that the variable that the pointer was accessing, this copy also accesses the same variable. Because when you think about it, a pointer stores a memory address, which gives us access to this variable. And so the copy of the pointer stores the same memory address. Even though they're two copies of the memory address, they will both lead us to the same place. So then we can access the same variable like that. So if we write our double function there differently, and we say the double's a pointer, and we get a pointer to an integer here, and we double what's in that integer, this will actually affect x. So we create an integer pointer, so remember the star symbol of the pointer, called pointer x, and we aim it at x, so and x is the address of x. So now when we're passing something into the function, we're not passing in the number 5, we're passing in the location of variable x, which means this thing can find the variable x, so num pointer is also pointed at the variable x. And we can double what's in num pointer, and that will actually affect x. So now this one, because we use pointers, x will actually get doubled to 10. Arrays are very useful, because an array, yes, is a variable. But the interesting thing about the array is that it acts nearly identically to a pointer when you pass it into a function. It actually has a bit more information than that. The array has a little bit of information where it knows roughly, well, no, not roughly, it knows what memory it has access to. So if we try to access an array and go outside of its memory, it'll tell us there's a problem. It's different from a pointer. A pointer is just like, here is some memory, right? Is my stream okay? I'm looking at my upstream, and my upstream is not quite as high as it usually is, but we'll see how we're going. I usually go at 8,000 kilobits, and we're going at like about 3,000 or 4,000 at the moment. Maybe the oh yeah, everyone's saying it's lagging a bit, and a few freezes. Okay, yeah, everyone's saying it's buffering. Alright. It's weird, I don't know, sometimes my phone is doing stuff, so I disconnected my phone from wireless, and now the bitrate is hovering back up closer to the normal thing. Okay, hopefully it's not too bad. I'll go back and watch the video later and see if it's too choppy. I'll re-record something. But actually just turning off my phone, disconnect my phone from wireless, seems to have helped there. And I am now concerned as to what my phone was doing that whole time. Apparently it's uploading a lot of stuff, and I don't know why. Okay, back to what we're doing. Arrays, the actual name of the array. So if we don't use the square brackets and we pass the whole array to something, the array's actual variable, what that is going to give us is the address of the start of the array. Which, when we think about it, if the array variable is storing an address, it can be used just like a pointer. Which means that when we pass an array into a function, we can actually affect the array elements, because the array that gets passed in the function, being a copy of the array that's in the main, for example, is the address at the start of the array. So this is why, and there was a confusing moment when we were working on arrays initially. There was this confusing moment where I told you about functions and passing in by value, and then also said that actually arrays are fine with this. Arrays don't have a problem. And so it's a weird situation there, because we had to tell you that everything was passing in by value except for arrays. But now you understand, because you know about memory addresses, you know why this is working. Yeah, and Raman's saying you realize this at that point. So there was a point where I hadn't taught you enough, and so there was this interim period in between where you weren't entirely sure why arrays were accessible via a function but variables weren't. But now that we've learnt enough about that, we can see why that is. So here's an example of functions with arrays. So we can have an array like this, and we can give our information to a function. The double all function is here, gets the length and then the array, and it goes through and it doubles everything in the array. And we can see that if we did this to the array 1, 2, 3, the array output, the output here would be 2, 4, 6. So anything we do to an array that's passed into a function is going to affect the original array that was given to it. So we're starting to get an idea of the nuance of what can functions access and what they can't. So everything that's passed to a function is passed in by value, but pointers that are passed in by value still give you access to something because they still contain the memory address of something elsewhere. So if we think about this diagrammatically, love that word, so many extra syllables. Let's think about the memory that's created when functions happen. So here's my whole program's memory, the green box. Obviously, as you can see, none of this is to scale, but every function that my program uses is going to have some memory. And in their own memory, they'll have their variables. So my main function has some variables that are declared. And if I call another function, so say it's that double function, or say I had a function that was going to, I don't know, draw a line on a canvas or something like that. When the function is called, its memory will be created. So it gets a chunk of memory that's inside my program's memory, and it's not the same memory as the main function. It's a separate piece of memory, and any variables it has, including the inputs that go into the function, will be created inside its own memory. So this means that the main function has its own memory space, and every other function also has its own memory space. And then an interesting thing happens. So this function ends. So I'm highlighting it in bold red here, that this function ends. When this function ends, we will then throw away the memory that was used for that function. Jay is saying there can't be a function inside a function, right? When we're talking about memory space, the functions each have their own piece of memory. When we're talking about calling functions, we definitely can. If you go back through my lecture examples, what's a good one that we had? The shuffler, the jumbler shuffler. That had a function calling another function. So the main called a function, that function called another function. Having said that, every time we call a function, it gets its own piece of memory. So this green box is actually much larger, usually, and we can just place memory for lots of different functions in it as they call each other. As they end, their memory will disappear, which means that any of the variables that are declared inside their function are taken with it when the memory is finished with. So the memory contains all of the lines of the function, in a sense, all the instructions, as well as all the variables. And so when they disappear and we go back to our main, then the stuff in here is no longer accessible. It's basically memory that's given back to the program to reuse to make other things with. So we can't, in a sense, create something in a function and expect it to still be there when the function ends. So this is an example of something that we might want to do, something that we think could be useful in terms of like style or repetition of something. So if I'm creating, let's say I wanted to do something with CS Paint and I wanted to have multiple canvases. And so I know how to make a canvas because I know that you set up an array and then you call the function that zeros the whole canvas or something like that. And I say, if I want to make 10 canvases, I don't really want to write that thing 10 times. So I want to put that in a function that's just like create canvas. The only problem with that is if I declare something like this, like a variable, inside a function. That variable's here, which means when the function finishes, that variable's gone. So this example where I say create an array, return the address of the array, so I'm returning an integer pointer, which is the address of the array, and I'm using the array's name for its address, which is what it does. We were talking about that a second ago. This function appears to create an array and then give back the memory location of the array that was created. The problem then is we give back a pointer to an array, which once we give back the pointer, once we return the pointer to the array, at that point, when my function finishes, the array ceases to exist. So what I do is I create something, and then I give something else access to a piece of memory that it shouldn't have access to, because that memory is just about to get ditched, in a sense. Oh, Kat, good answer. So there was a question there about can there be a function inside a function? All functions except for main are actually inside another function. It's a good one. People are saying that there's lag. I've got full uprate going now. Hopefully that's okay. I'm not sure. Yeah. And Raymond's saying, can we return multiple variables from a function? We can and we can't, right? So we can never return more than one variable from a function because the function has a type and that's the only thing that it can return. However, if we have pointers to things and the inputs to the function, we can access variables that are elsewhere. So in a sense, we can give back more than one thing, but it's not really giving back more than one thing. Yeah, my bitrate is dropping again. I'm not sure why. Well, we have to keep going. And hopefully you can still hear what I'm saying and you can still understand what I'm talking about, even if there's a bit of buffering going on. Okay, so we have a situation here where we can't keep something that we've created in a function, even though we might think it could be really useful to keep something we've created in a function. So then we get on to a new way of doing things, which is memory allocation. So Nayuki's saying that they're using the CSE VPN at the moment. I think the downside to that is I'm not on the CSE VPN right now because I'm just streaming from home. So my stuff is going straight to YouTube and going out onto the internet via that. So whether the CSE VPN actually makes you faster or not for accessing my YouTube stream, I don't think it necessarily will. Even though you might be linking to it via WebCMS, that's still taking you to YouTube where I'm streaming from. Hopefully the recording is fine as well, and it's all not too buffered when we do that. Okay, so I wanted to introduce a new function to you. It is called malloc. It is not a biblical demon. It is short for memory allocation. And it takes in a certain amount of bytes of memory and it will give back a pointer to memory somewhere in my program's memory. The thing that it will do, which is really interesting, is it allows us to say, here is a chunk of memory. I want to set aside that chunk of memory for my use. So I want to say, dear program operating system, please give me a piece of memory and don't take it back automatically. So I'm going to ask this inside some curly brackets somewhere, and I want this piece of memory to disregard the normal rules for curly brackets. I want it to be my piece of memory that I can use for many different things, and I'm going to set it up and I'm going to be careful with it. And it won't automatically get cleaned up. So it won't be like this piece of memory here that automatically gets cleaned up. So because it won't get cleaned up automatically, we will clean it up ourselves when we're finished with it. So when I have passed it to multiple functions and it exists nearly outside the scope of any of the functions, when I'm finished with it, I will give it back by freeing it. So I'm claiming a piece of memory by allocating it, and then I'm freeing it when I'm done with it. So we're going to go through and show you how this works. But it's important to just kind of get to the idea that we're going to grab pieces of memory, and these pieces of memory are going to become special. And they're going to be these things that we have control over, that the program has less control over, which means the program becomes potentially a little bit less safe because we can do this, but potentially we can get more functionality out of things because we can do this. We just have to remember to clean up after ourselves. So every piece of memory we take, we eventually have to give back. When we get down to it, we're actually going to end up going through our code and counting the number of times we call this function and making sure we call this function like the same number of times. And it gets a bit confusing once we start doing this with loops. So let's think about what this can do. Same diagram. Function called by main. When we assign memory with malloc, it is not inside a function. So it's neither is it inside my main function, nor is it inside this other function that I called that was going to be called by main and was going to actually run the function malloc and assign memory. So when we allocate memory, it's somewhere in our program, but it's not necessarily inside any of our functions. So now what happens is this function finishes, and let's say before it finished, it gave the pointer to my main function. So it said, here's the pointer that I got from the malloc. So the main function now has that. This memory is still usable. The memory that was allocated, even when the function gets cleaned up, this memory still sticks around. So long as we have a pointer to it, we can keep access to it. So this now gives us the capability to create something that doesn't just automatically disappear. I mean, usually the stuff automatically disappearing, that's actually a nice thing. So sometimes we think, well, why don't we just make everything never disappear? And it's like, yes, some programs do work like that. Like once we get more advanced, we can actually write programs where all the memory is always available to us. But they're a bit more dangerous because then we can do things by accident that exist outside of where they should exist. And then we can access the wrong variables and things get really messy. But in this situation, if we go, okay, here's this variable, and there's a pointer to it that we can access with our main. So we keep access to this piece of memory past this thing leaving. It gives us the ability to create things in functions, which means we can space out our code much more nicely, and also we can pass around pointers to things instead of copies of variables. So there's a lot of benefit in doing this. But as you can see, it's the kind of thing where we really need to learn a lot about how memory and functions and stuff work before we can even get to this point. Eric is asking, malloc is like a predefined C function. Yes, malloc is a function that is from the C standard library. So we're going to be doing a hash include from the standard lib in all the programs that are going to use malloc. Kavan says, sounds like Murloc. And Jamie's saying, what happens if you forget to free a pointer? We'll look at that in a moment. Jamie is asking, does the program just hold the memory hostage? Yes, the program will hold the memory. If we lose, if we allocate memory to something, and this pointer here, if we didn't give this pointer back to the main function, then we still own the memory, but we won't know where it is. So we'll have memory that has been allocated to us somewhere on our computer, but because we didn't keep the pointer to it, we don't know where it is, we can't use it, we can't even free it and give it back, but it's still allocated to us. So you can actually get to a situation where your program just eats up more and more memory by allocating things and losing them, and then eventually it's like your computer runs out of memory. We call these things memory leaks, and they are quite important. You will see these kind of old ideas, like, did anyone ever use, like, I don't know, like Windows 95 or something like that? Or even the earlier eras of operating systems. It's not just Windows. Windows is the most famous one. And this is where the phrase turn it off and on again came from, because the operating system actually had memory leaks in it. So memory leaks are a situation where you've assigned memory, but you no longer know where it is. And so eventually it would have all of this allocated memory sitting in your computer's RAM, and it would just be eating up more and more of it over time. And if you left this thing running for a few weeks at a time, you'd actually run out of memory and not be able to run any programs because there was no space left. All the space had been allocated to things that had forgotten that they owned it. And so turning it off and on again would actually reset everything so the memory wasn't allocated anymore and your computer would start running again. It's not precisely that, but it's a very, very similar situation. And so like a lot of older systems had things like this stuck in them. I mean, I've got to be honest, a lot of modern systems also have this problem because allocating memory and forgetting to free it is a very human mistake. So we can do this very easily. You will be doing this when you're learning about allocating memory. Sorry, I just realized my face was blocking some of the words there. But we'll talk about that in a second. I'm going to talk about how to make it, how to allocate memory and stuff, and we'll actually, if I get time, we'll do a demo on memory leaking as well. Alex is asking, is that what Chrome does? Chrome is smarter than that. It doesn't have memory leaks, but it will use all the memory that it has available. So every tab it will try to keep in memory so that it's quick to move between tabs. And the more tabs you have, the more memory this thing tries to use. So Chrome is thought of as a memory hog because it uses up a lot of your system's memory. But it's not necessarily losing it, because I know that Chrome's actually built very well, but it's also built to use as much resources as it can possibly grab. So there's a bit of slightly different to losing it, it grabs it. And Girichan saying in 2511 you learn more about things like this. As Miguel's saying, yeah, we're not really sure that Chrome is leaking memory, but it's more that it's greedy with memory. It uses as much as it can. So when the program finishes, it does actually get all of its memory cleaned up, including all the memory allocations. Having said that, I still want to make sure that we clean up everything that we can ourselves, because we need to learn how to make sure that our allocated memory is freed properly. Anyway, let's get into that. Let's get into that bit by bit by actually learning how to use this. So I'm going to teach you something else. This operator called Sizeof. It may look a little bit like a function because I put brackets on it. It actually doesn't. Actually, you know what I'm going to do? It doesn't actually need the brackets. That, I think, would usually be this. Sizeof is an operator. It is not a function, but it's an operator because it doesn't take inputs the same way that a function would take inputs. It takes a type as its input. I'm going to say input in quotes because it's not an input. Sizeof allows us to look at a variable type and say how big is that variable type. So, for example, we know this already that an integer is 32 bits of information. A double is 64 bits of information. An array is a multiple of the size of the thing that's being stored inside it. So your canvases in CS Paint, the 2D arrays in those are number of rows multiplied by the number of columns multiplied by the size of an integer. So if we wanted to, when we were doing memory allocation, I could actually just give it a number. So instead of saying size of int here, if I know the size of an int, it's 4 bytes, because each byte is 8 bits and an int is 32 bits, I could put the number 4 in here and I would get the right amount of memory from an integer. Having said that, I want you to do it this way because it's much easier. We're going to kind of head off all possible mistakes we could make with this thing by always using Sizeof. So this line is a line we will get used to because every time we are going to use malloc, we're pretty much going to be writing exactly this line. So the function malloc will take in the size of whatever it's aimed at. It'll be a variable type. And when we get to it and make our own variable types, we can throw these in here. And what Sizeof will do is at the point this thing runs, it will say how big is this variable type. And it will go through and it will check how big the variable type is and say, okay, that's how big it is. We can guarantee we always have the correct variable size, the variable type size here by using Sizeof. then malloc will get that much memory for us from somewhere in the program. We're not too worried about where exactly in the program that is. We allow the operating system to organize this stuff for us and just go, okay, here's a chunk of memory for you. There's a whole lot of back end going on here that we don't even talk about. I think it's a 1531? No, 1521, I think, where we go into the lower level and where the stuff is actually done. Sorry, I'm talking about further computing courses at CSE if you're interested. The type of the pointer is always the same as the type that has been memory allocated. So if we memory allocate enough memory for a particular type of variable, that is the type of variable the pointer is. So the types match on either side. So we'll always have a pointer to a variable that we're memory allocating. And so this is going to look the same every time we do our memory allocation. And then we can say, once we've got that, we have a pointer to a variable. Just because it's a piece of memory that's outside of our functions doesn't mean it's not a variable and it's not accessible just like a variable. So if we have a pointer to a variable, we can do anything we can normally do with a variable. It's the same as if we gave a pointer to a function. That function would be accessing variables that are outside of its memory and outside of its scope, but it's okay because we had a pointer to do it. malloc is the same thing. These variables exist outside of anyone's scope in our program, but we just use the pointer to still access them. And from then on, we just start to think of them like a normal variable. The only thing we need to remember is later on we need to clean up after ourselves because they're not inside any of our scopes. And here's the cleaning up after ourselves. We use the function free. This is a really simple function to use because you don't need any of the kind of parameters that malloc needs. You don't need size, you don't need to store it in a pointer or anything like that. You just say, there is a pointer to something that I allocated. So I've got a function here called malloc number, which is this one, that says malloc an integer, set it to 10, and then give back the pointer to it. So this is this. So we are assigning some memory with memory allocation. We're giving that pointer back to another function. So nearly this diagram is exactly the same as what's going on here with malloc number. So if we've called malloc number and we've stored the pointer, then we have access to that variable. We can do stuff to that variable. I just put some random code in here. You're probably going to have a lot more code in here, a lot more other stuff that you can do. When you are finished with that variable and you know you don't want to use it anymore, you free it. So you say, that variable that I made specially, it's not necessarily going to get cleaned up properly, so I need to clean it up myself, so I free it when I'm done with it. So again, as I was saying before, every time we malloc something, there's going to be a free somewhere. So it's like, I grab this thing for myself, and then I give it back when I'm done. But I have to explicitly give it back, as opposed to all the other variables we've made up until now, where we just say, here's a variable, I've declared a variable, I am giving that variable back, but I'm giving it back automatically when I hit the closing brackets for the current scope that I'm in. This variable, however, hits these closing brackets and it says, because this is a memory allocated variable, it doesn't get cleaned up automatically, so it can go back here after the function's finished and I can keep using it. But then if it hasn't been cleaned up the way it normally would have, I need to give it back at some point. So here we have the situation following on from where we were before, where the memory is still usable, the main function's now using that memory, but I say, okay, now I'm done with it. When I'm done with it, I call free on the pointer, and the pointer goes to where the memory is and says, all right, let's give that back. And once we've given that back, the program is free to use this memory now for other things, because the memory has been kind of released back to the program. What do we, I'm just looking at what people are saying at the moment. David saying, can't convince me that turning a computer off and on again isn't an eldritch ritual. Yeah, a friend of mine used to talk about the blue smoke, saying that the blue smoke in the computer was the magic that made the computer work. And then you know when a computer's broken when the blue smoke comes out. The blue smoke is when your computer shorts and burns part of itself. It's like, things melting in your computer, but he used to say that the blue smoke contained inside the computer was actually what made it work. Nasa's asking, why don't we use the star when returning the pointer? So, what do you think that we would be getting back if we returned a pointer with a star on it? So remember what the star does with the pointer. The star says, I'm going to follow the pointer to the variable it's aimed at, and that's what I'm going to use. So if I returned a pointer with a star here, I would not be giving back an integer pointer. So let's go in here. If I returned this, I would not be getting back an integer pointer. I would be getting back the number 10, which is what's inside the integer pointer. Because remember, the star says, I want to follow the pointer to its destination and then use what it's at its destination. At this point, because I'm giving back an integer pointer, I want the pointer itself, not what it's aimed at. So if I want it itself but not what it's aimed at, I need to give it only its own name and not the extra information. Jamie, praise the Omnissiah. Oh yeah. Warhammer references. People know that they can use the Warhammer references with me. Oh. Zeal's been reading The Three Body Problem. I only just finished reading that recently. It's a really good book, by the way. It's really, really deep, full-on sci-fi. Anyway, let's continue. Oh, Stefan's saying, so by freeing the pointer, is the pointer not accessible anymore? Yeah, so that's something we've got to be really, really careful with. If we free something, the pointer is still aimed at that memory after we free it. Free does not affect the pointer. Free goes to the thing that's at the other end of the pointer here and makes this memory no longer accessible, which means this pointer is now aimed at pieces of memory we can't use. So there's an error that we can get, which is called use after free, where we accidentally use something after we've freed it, and that's really weird because we can't access this pointer anymore. We would have to either throw the pointer away or change the pointer to be something else. Like we could say that pointer is null afterwards to say that it's not aimed at memory, or we can move that pointer to aim at something else if it needs to. Sometimes we will just never use that pointer again afterwards, and we'll let the curly brackets clean up that pointer whenever. Yep. Kat's asking, is a memory address an integer type? Kind of. A memory address is definitely an integer. But it's not an integer type because it's 64 bits, not 32 bits. So the type is not just the numerical kind of properties of something, it's also how much memory it uses. So a pointer is a 64-bit whole number. So I'm going to use the term whole number, even though I know whole number and integer mean the same thing mathematically. For computing, they don't, right? So it's a 64-bit whole number that represents a location in memory on our computer. Whereas an integer is a 32-bit whole number that represents some kind of numerical value. So you're right in a sense that a memory address is an integer, but it's sort of subtly different. Raman's saying, is all of this week's knowledge going to be needed for the second assignment? Yes. This week's knowledge is the lead up to the second assignment. So what I'm going to be teaching you on Friday is the fundamental data structure known as a linked list, which is what this is leading towards, and the linked list is what we're doing in the second assignment. Okay, so things we need to think about. Every time we're going to use memory, we're going to use Sizeof to figure out how much memory something needs for the memory allocation, and we're going to use the same type in the Sizeof as the pointer that we're going to save for that memory. Oops. Structs are coming. I changed the order of things last minute. I forgot to say this word out. We can allocate any kind of variable in memory. So yes, we can allocate collections of variables like arrays. Structs I'm about to talk about that we can allocate. I would say always use Sizeof with malloc. And to remember, you must always free everything that you allocate. I'm adding now a new tag to DCC. You can do this with or without the hyphen, it still works. Leak check. So we'll put our file names in, our file name that we're reading from, file name that we're creating, and if you add leak check, it'll tell you at the end of your program running, it'll tell you whether there was any memory hanging around at the end. The program will clean up this memory on its own when it finishes, but I want us to clean up all of our memory all the time so that we get good practice for cleaning it up. So sometimes you may end up in a situation in the future where you write a program that doesn't just end when it's finished running. So like all the programs we've been running so far is you type in some input, the program ends. But when you think about some programs that we might run on our computers, or we might run in an industrial setting. So think, for example, about an email server. So a program that's there to manage the emails for a company or an organization. So all the emails that go to that company's domain will get sent to this email server. It will process it and send it to an individual person. That program runs perpetually. It's going to stay up forever. And in staying up forever, it will, if it has any memory leaks in its processing. So let's say it drops a tiny bit of memory every time it processes one email. Eventually this thing will leak because I don't know how many, like average company, thousands of emails going around a week, thousands of tiny bits of memory. Eventually it will lose all of this memory, and then the computer that it's on will have no memory remaining, and it will crash, and then your email server will die. This is not something that happens that much these days, but has definitely happened in the past. So what we want to do is get into the habit of making sure that anytime we grab memory, we're giving it back. Hi Shrey, how's it going? Actually, you know what? Before we go to the break, I wanted to show you some code. Because we've got a couple of minutes before my planned break time. I guess I could go early, but I want to show you a couple of things about what may happen with memory. So we're lecture 11. Oh wait. COMP1511. Let's go into lecture 11. I've got some stuff in here for the demo for later, but let's make something new. Okay, so I've just made something called memory demo. Oops. Ooh, 1611. I've just been upgraded. Okay, let's include the standard library because we're going to be using our memory functions, and I've said that those are in the standard library. I realized I didn't actually say in the slides where we get malloc from. So let's do some memory allocation, right? So if I want memory allocation for an integer, I'll store it in an integer pointer. IP, yeah, IP will do. And I'm going to malloc, and if I want to memory allocate something, I have to say the size of the thing that I'm memory allocating. Sizeof int. Alright, so this will allocate one integer's worth of memory. I thought it might be funny to show you some memory leaking. So let's accelerate our memory leakage here. So I do have some demos of memory being used, but here is, let's do the most dangerous thing. So here's my program. This integer pointer will be created and will immediately disappear. However, this memory will not disappear. Girachan's like saying, this stream is about to crash soon. Sean's asking for the assignment 2 information in the form of a wrap. I would have to rewrite the spec that's nearly already written now. Oh, the second assignment is releasing at the end of this week. It was in my notice on Sunday, but we'll tell you all about it when that happens. Okay, so people can already see some of the issues that are probably going to happen here. I'm going to allocate memory. I'm going to immediately lose it because I didn't save this pointer anywhere. I'm going to go back to the start of the loop. This loop will keep going forever. And then I'm going to allocate more memory. So let me set up this situation first so that we can see what's going on. Okay, I'm going to run a program here called top. This is something that Linux has available to us. It will tell us what our programs are doing. So I've got top here actually running. It's using 0.7% of my CPU and 0% of my memory. XFCE is my desktop system. There's all this kind of stuff going on here. Oh no, XFCE terminal is one of these two terminals. I don't know which one it is. I assume it's this one because this one's doing work at the moment. This one's doing a little bit of work because in the background this one's running my gedit window. But what this is going to do is allow us to watch our system and see what our system is doing. So what I'm going to do now is DCC my memory demo. I'm going to call it memory demo. I guess I should probably compile this with leak check. Although you can probably already see that since this program's never going to end... Oh, sorry, I was supposed to put brackets around what I'm checking in Sizeof. So let's go and put this in this format so it looks a little bit like a function. It's not a function though, it's just going to look like one. Okay, good warning. And you should be listening to the warnings in your programs. Unused variable integer pointer IP. So all I did was set that to a location and then I never used it. And this should be a warning sign because if you've memory allocated something and never used it, it means you're not freeing it. So this is going to leak memory. What it's going to do is it's going to grab memory for a single integer. And then it's promptly going to throw away the address. So it's kind of like it's going to grab some memory, and it's going to grab some more memory, some more memory, some more memory. That's what it's going to do when it runs. So, let's run this. So the program's now in an infinite loop. Let's have a look here. It's using 100% of my CPU right now. And look at this. This is memory residence. This is how much memory it's using. We are currently at 3.6, 4.3 gigabytes, 5.1 gigabytes, 5.8 gigabytes, 6.6 gigabytes. This is all the memory we're allocating. We're allocating so much memory. 7.5. Oh, we've disappeared. And we get this single word here. We don't get any other information. Just a single word here saying killed. So the operating system has looked at all the things that are running on my computer. Well, this isn't my computer, this is VLAB. So this is someone else's computer. This is a CSE's computer. F for respects. The thing that we're getting here is the operating system that said, you've used up too much memory, you can't have any more. You've run out. So at 8 gigabytes, it said, you've run out, I'm not going to give you any more, so I'm going to end this program. So this is a really, really accelerated version of what can happen to you if you're leaking memory in your program. So leaking memory inside loops that are perpetual. So like that situation, like that mail server that I was talking about, this could end up in this situation. And a mail server is not the kind of program that you want to have this happen to it, right? We want these programs to be reliable and to keep running. Someone was asking what top was. Top is just a program that allows you to see everything that's happening on your computer. So each one of these are all the programs that are running on my current login of VLAB at the moment. So there's even more stuff happening here. Like there's like a screensaver, there's a desktop thing. There's all this random stuff going on, which is just part of how this windowing system on VLAB actually just shows us everything. So there's something there for volume, there's a screensaver, there's all these different settings and stuff. So they're all these tiny separate programs that make up what we can see. I was only really worried about the things at the top here. That's not a pun, but that was not intentional. The things at the top, which were the things that I was currently using. So these are the things with the most activity. So my terminal and the actual top window here. So I'll close that because I don't need that now. I think I've shown you what happens there is that if we're not sure about what we do with our memory and we're not freeing it, we can use up a whole lot of extra memory. Actually, if I just do something really, really simple, like this, I use it and then I free it immediately. Let's run this now. So we've still got an infinite loop of memory allocation, but I'm giving back each piece of memory. So I'm not going to be necessarily continually leaking memory. So this is now infinitely looping. Let's see what my computer looks like now. So memory demo, memcheck is what's going on in the background because I compiled this with leak check, but memory demo is my actual program. We know that because that's the name of it. It is using 100% of the CPU that I'm running on at the moment. Its memory, so this is what we call the resident memory that it's using here, is 73K. So it's using 73K to set everything up. But otherwise, what it's doing is allocating memory, then freeing the memory, then allocating memory, then freeing memory. So that kind of thing. All right. So there are some examples of the stuff that we do with memory allocation, and just an example of what happens when it blows up. Later on today, I'll show you examples of us actually doing some stuff with it. So let's go on break. Oh, I'm the wizard. So I'm going to put my face here. So one thing to remember, memory allocation can be tricky. And sometimes you can actually forget where you've allocated memory and forget to free it. So that's one thing that we need to keep in mind. Trent's asking, how are we using 99% CPU for memory demo and memcheck simultaneously? I have a feeling that the thing that's running my code there was probably running multiple processors, and it measures the percentage of each processor separately rather than the percentage of all the processors added up. So I was using all of one core in the processor on one part of it and all of one core on the other. I think that's the way that would have been measured. I wasn't actually looking that closely at that, but I think that is. Okay, I am going to go on break now. We'll come back in 5 minutes at 12:09, because it's 12:04 now, and we'll go on to Structs and do as much of a demo as we can on using Structs and memory management. See you soon. Alright, I'm back. Oh, I should move my face. Okay, so continuing what we're looking at today to a slightly different topic. These things are called structs. I have an image here of a bento box. I always like this little analogy. Because a bento box is a meal, but it's a meal not made up of only one type of food. It's all these different types of food, and they're all pieced together and they fit nicely in this little box. And that's exactly what a struct is. A struct is a thing that we can create, which is a custom variable type. Actually, it's not just a thing, they are many things that we can create that are custom variable types that are made up of other variable types. So, up until now, we've been collecting variables together in arrays. So we had a collection of multiple variables, but they were all the same type. Now with a struct, we can collect multiple variables together, and they can all be different kinds of variables. So that's why I like to think of it as a bento box. You can have some rice, you can have a bit of eel there, you can have some salad, there's some salad over here as well, some of your preserved veggies and stuff like that. So you get lots of different kinds of things and bundle them together. So we are going to actually be defining our own variable types. So these are going to be things that we're defining in a similar way that we define our functions before anything in our program uses any of these functions. We are going to define our own custom variable types in these structs and then use them. So for example, Sean's saying stop using food food analogies. I apologize also because I keep doing food analogies during our 11 to 1 p.m. lectures. Look, to be honest, I'm also hungry during these lectures. Like, I fill up my stomach with water during these lectures to try to suppress it. But okay, so this is how we do it. So I'm going to use this example here. If anyone's seen Avatar: The Last Airbender, I made this example last year when it came out on Netflix and I was re-watching it. So a lot of what we're going to talk about is going to use some of the stuff from that. But let's have this idea that we have these characters that we want to create information for. And so we want to collect all of that information together into one variable. And so for this, we may have a person who is a bender. They're called benders in this particular TV show. And they have a name, which is a character array, a string, which is of a certain length. Let's assume that I've hash defined this somewhere. And they have an element that they use. So they have in this particular TV show, there's 4 elements that they use. And each one of them will use a certain element and they have a certain amount of power. And so this definition of the struct is something that we would set up at the start of our program, and then from then on, anywhere in our program, we can actually treat this pair of words, struct bender, as a variable type. So anytime we use struct bender, it means a variable that consists of one string called name, one string called element, and one integer called power. We can put all kinds of things inside these structs. Any variables that we want, we can put inside these structs. I think some people there know about Avatar: The Last Airbender, which is cool. Okay, let me put my face somewhere where I'm not. I'll move over a bit, not covering up any of the text. So, the way that we would use a struct variable is the type is actually 2 words now. And so this shouldn't be that alien to you, the idea that a type can be something more than just a single word. So we had a single word types for stuff like int and double and things, but once we started using pointers, we were okay with having a variable type that had spaces in it. So now we have a variable type that has more than one word in it. So the struct is the keyword, and the struct keyword says I'm about to tell you about a custom variable type. So struct says to my compiler, here's one of my custom variable types, and it's going to be bender. So assuming that this has already been defined earlier in the program, we can then use it inside the main function by saying, I would like to create a single variable of the type struct bender. So if I have a single variable of the type struct bender and I'm calling that variable avatar, and then I'm going to put some information in that. So in order to fill out strings in something like this, we need to copy strings in. So strcopy from our string library is something that will just do instant copying of multiple letters rather than us having to write a loop and copy them in one at a time. So I'm calling the avatar ang, and the avatar's element is going to be air, and the avatar's power is going to be 10. And if I print this out, I can access the individual variables inside the struct by putting a dot after the struct name and then accessing what's inside. There's actually multiple ways we're going to do this, but I'll show you the dot and then I'll show you the other way in a second. So what this will do is we'll say, go to the variable avatar. The variable avatar here is a struct bender variable, which means as a struct variable, it doesn't really have its own value. It contains things that have their own values. So the name inside the struct has a value, the element inside the struct has a value, the power inside has a value. So if I want to say this person's element is this, I say this person dot name to access the string inside, and this person dot element to access the other string inside. So if I say the struct name dot the field name, they're called fields inside the struct, this is the same as getting access to a string variable. The actual string that it's using is this one in here. So long as you set this up as we have here, and we've put the value in to the name, we'll get it back out here. One thing that we're going to be doing a lot though, and this really ties in with the stuff that we're doing with memory allocation and stuff, is very often we're going to be doing where we're going to be memory allocating our structs, because our structs can get big and unwieldy, and this is why these are both in the same lecture. So most of the time we're going to be memory allocating our structs, which means the only way we can access them is via a pointer. Things that we could do with pointers to think about this, and this gets really fiddly if we have to do it this way, where we say go to, so let's say I have a pointer. Oh, that's a typo. Hang on a second. I've made a pointer here, struct bender pointer called last airbender. This should have been last airbender, as this should also have been last airbender. Apologies. Let's go back to that. Okay, so I have a pointer here called last airbender. So if I'm accessing a field inside a pointer, the first thing I need to do is use the star on the pointer to get to the struct variable. So if I use the star on the pointer to get to the struct variable, once I've done that, that actually has to go into brackets, because if you do it the other way around, it actually goes to the dot of something and then tries to do the star. So this is a bit fiddly because we have to do it in brackets. And we say, go to that pointer's variable. So this takes us to the avatar variable, and then take its power and make it 100. So we're going into avatar state here. This is so commonly used that we replace it with a shorthand, and the shorthand stops us from making mistakes by leaving out the brackets or doing anything accidentally accessing the wrong pointer and things, by just saying, if you have a pointer to a struct and you want to access one of the fields inside the struct, you use the arrow. So we're going to be using accessing the things inside the struct by one of two methods. If we have a variable here, we use the dot. If we have a pointer to a struct, we use the arrow. So there's two ways of doing it. The way to kind of remember it is, if we have a pointer, we use the pointy thing, the arrow, to access it. If we don't have a pointer, we use the dot to access. So these are the two ways we access the actual variables that are inside the struct variable. Oh, sorry. That's the same. I had more information on the same thing here. I don't think I need to talk about this. The other thing that we're going to be doing a lot And this is the same thing as saying like why we would use pointers for structs a lot is A, we're going to memory allocate them a lot, and B, we're going to be passing pointers to structs into functions a lot. So if we pass a pointer to a struct in a function, we're also going to need the arrow to access the fields inside the struct. So if I had a function here that was going to display a person, it was going to print out their name, the element, and their power, I would use the arrow because the access we have to this person is a pointer. Kat obviously knows this TV show well. That is kind of the opening, but with a programming perspective. Okay. Oh. Let me just move my face. All right. So, structs are our own custom variables, but they will be acting exactly as variables. So they're going to work the same way that we would work with something like an integer. The only difference is we're going to be poking inside them to get information. But what this means is if a struct is a variable, then we can make arrays of structs. We can make pointers to structs. We can do all the things that we can normally do, we can do with structs. So once we have defined that a struct is a certain thing, then it becomes a variable type for use anywhere else in the program that we've created it. So let's go into an example of forming a team of people with special elemental powers. These people are called benders. And we're going to make a struct that represents an individual bender, and then we're going to make a team of these benders where we will do something like have an array of pointers to the memory that we've allocated for the individual members of the team. I don't think we're going to get much further than that. I do have another example, which is structs and pointers, which actually has the benders getting in a fight and things like that. But I think in the 40 minutes we have here, we're not necessarily going to get time to do all that. But what I'm hoping is that we can show you some use of structs, how we can put things in structs, how we can access things in structs, and how we do memory allocation for structs. So the first thing we're going to do is create the structs for each of the characters. And we saw this a second ago. This is the one that we saw earlier. So let me just hop back in here. Oh, that's still running. Oops. Sorry, VLab. Anyway. My infinite memory allocation was still running. But that's okay, because at least the version that was still running was the version that wasn't leaking memory. I mean, that one would have gotten killed by now anyway. It's alright, all I was doing was using a lot of CPU. And I think that when a program uses a lot of CPU like that, I think our system support people don't even worry. They're like, you know, especially if it's like, oh, Mark Chi's account is running an infinite loop. It's like he must be in a lecture doing something. That's what I hope they think of me, rather than when I'm writing code for myself and it has infinite loops in it. Okay. So what I've got, actually I'm not going to show you this. This is the finished version. I was doing this earlier, so I'm going to move the finished version to another directory. I'm going to make a directory called finished, and I'm going to move, I'll show you something cool. Move bend star to finish. This will move all three of those files. Yep. So if I go into finished, just stepping aside for a little bit of Linux stuff here, I'm in finished now, and all three of those files, because they all started with bend and had some other letters afterwards, that's little tricks that we can use. Okay, go back to where we are, and I'm going to make a new one, because I want to build it from scratch with you, rather than... There's always, somewhere on my computer, there's always some... This is something I prepared earlier, but it's very rare that I'm just going to dump on you something that I prepared earlier, unless it's something that's going to take too long in the lecture to do, and I just need to show it to you. So I think I did that with some of the scanf demos, because there were so many things. But legitimate demo like this is something that I want to build up from scratch. Okay, I can close that memory demo. A demonstration of structs and memory allocation. I don't know why that's auto-completing to demons. Very weird. There's something going on in my computer. I think this is our last lecture in October, now that I'm looking at it, because I think next time we see each other it's going to be November? Maybe? I can't remember. Maybe there's one more in October. Okay, so I know that I'm working with memory. So I'm going to include the standard library. This is the C standard library that has a lot of basic functionality for C in it. I'm going to assume that I will probably be using standard input output as well, so we might as well include that. I mean, it's going to be hard for us to do anything and see what's happening without it. I won't use command line arguments for now. Okay, so here's our basic program. For us to be able to use a struct, we have to know that it exists, so the struct has to be defined before any of the functions that we use it. So what we usually do, so now we're actually starting to pile up the things that we do beforehand. So we'll have our structs, and we'll have our functions. Obviously, you don't need to necessarily put these headings in when you're writing your code, because we assume that we know the difference between structs and functions, but I'm going to put these up here now so that we remember what we're doing. So struct bender has curly brackets. Weirdly, slightly different from other things that we might do, it has a semicolon like this. A lot of our curly brackets don't have semicolons, but when we're declaring structs, it's considered to kind of be a single line with a semicolon at the end saying, okay, this is the end of that. We were making a character array called name, another character array for the element they're using, and an integer for the amount of power that they have. These character arrays I cannot leave open like this. I can't leave them as like indeterminate length. The struct will have a specific size in memory, so I need to declare when I'm making these how big they're going to be. When I'm working with just size of things that I'm not sure exactly how big they're going to be, I will work with a define. I'm going to call this max length because it's the length of the strings. Just to be on the safe side, 1024. These magic numbers that we often use in computing, they're all powers of 2. I very, very much doubt that any of these are going to need to be 1024. But I'm doing this out of safety's sake in case someone wants to write someone's entire backstory in their name. But I doubt we're going to get to 1024 characters, but sometimes it's better to be safe. So there's my max length there. Okay, so here's my struct for an individual bender, which means I can create a variable of type struct bender now, and that variable will have enough space to store these two strings, so each one of these will be 1024 characters, and an integer. Isaac saying, let's all run this. Please don't all run the memory allocation program on VLab at the same time, especially not the bad one that leaks memory. And Girijan saying, all the other comp students are probably wondering why VLab is so slow. We do actually have issues like that where if we run an exam on VLab with, say, I don't know, the biggest course in CSE gets up to about 800 students. When we have 800 students all running an exam on VLab at the same time, we need to have a conversation in advance with the system support people and let them know. And then they will kind of divert some of CSE's processing resources to make sure that everyone's works. But we're capable of doing that. Like, for me to try to break VLab with a single login, it's nearly impossible. Because I could use, as I did then, 100% of CPU, 100% of memory, and all it does is kills my process. You know, so it's much harder to take down something like VLab. VLab was built for scale. Strangely enough, here at CSE, we do have some very, very good engineers working on the back end. Okay. Yeah, and Miguel's saying we get one processor. I think we get more than a single core, but we're limited to 8 gig of RAM per program that we run. Okay, so with this struct, we can then do something like we were doing before. So I could say struct bender avatar is a variable, and then I could do things like string copy. If I wanted a string copy, I'm going to need the string library. If you ever need to look up some of the stuff, we have a sort of an abridged version of what's in the C libraries, like a version that's made just for people learning about C in the cheat sheet. So you may have seen the cheat sheet in the weekly tests. If you go to the weekly tests and grab the cheat sheet, you'll actually get some really concise information about these libraries that kind of takes out a lot of the extra functions in there that we don't need to know about at this point. So that might often be a good place to start thinking about the things that you can do with these libraries. So if I had the avatar there, I could do string copy, for example, avatar name. Oops. Just made a smiley by mistake. Okay, so I can do this kind of thing. So I can say, make me a variable of this type. So this becomes a type. Once this definition is complete, everything afterwards can use this type. So I can create that, which is going to create a variable with all of this capability. And then I can start messing with what's inside it if I want. Let me show you something cool. All right, so I said, this is now a variable, which means if I want to, I can make a struct that refers to that struct. So I can make a struct for a team, which has, say, a team name, the number of people in the team, and then this is probably this I think is probably the most complicated single variable declaration that we can possibly have with what we know in 1511. Actually, no, we could have made this two-dimensional, but what we've got is a struct type pointer, so a pointer to a struct called team members, but it's an array of pointers to structs. So we've got an array of pointers to structs, which means we have an array that represents our team. Each element of that array gives us access to a piece of memory where a member of our team is. So we're going to have this team struct, which is able to use the individual bender struct and have multiple pointers to these individual benders. So let's declare another struct here, which is for the team. And the team will have a name. We'll have a number of members. And then we'll have that interesting variable. So it's an array of benders. And then I'm going to need to know how many people are in a team. Team size. I'm going to start with 3 because I just don't want to manually type in the names of more than the 3 characters. I'm going to start with the 3 characters from the beginning of the show, no spoilers. Team size. But this is not going to just be an array of benders. So instead, I'm going to do, as I was doing here, it's going to be an array of pointers to benders. And its name's going to be team members. Alright. So yeah, this is probably as hard as it gets in terms of individual variable declarations. So if we think about it from the name outwards, the name is team members, and it's an array of size 3, so there's 3 members on this team. Each member of this team at this point in the team is represented by a pointer to a struct bender. So I'm using an array of pointers here so that what I can do is I can allocate memory separately for each of these things and then have pointers to them. This isn't always the way that it's done. I'm doing it this way to show you a bit about how we can allocate memory and do stuff like that. So, in order to set up this team, I'm going to get rid of that, what I was doing there. In fact, I'm just going to throw some white space in there so that we can see where we are. I'm now going to build up this information. So, one thing that I could do, and this is something that kind of leans into what we were talking about before, the idea of if we're going to memory allocate, sometimes we're going to memory allocate in a function. So I'm going to make a function here that is going to create one individual bender by taking in a string for their name, a string for their element, and an integer for how much power they have. And it's just going to simply do the initialization. So when we think about initializing a variable, it's really easy because we just throw in a value and it appears. When we think about initializing a struct, it's much more complicated because a struct can have all these variables inside. So it makes more sense for us to throw this into a function than it is for us to actually do this bit by bit. So instead of just going string copy this, this, if I want to do this multiple times, I want all the string copy stuff to be put in its own function. So let's create a function. And there's actually a reason why I did these headings, because if you look at this, I'm going to return a pointer to the bender because the create bender function is going to do some memory allocation. If it's doing some memory allocation for a bender struct, we must always preserve the pointer that it used for the memory allocation. And we've already seen today what happens if we forget the pointer. If we forget the pointer to something we've created, we have a memory leak, and then stuff is just memory is just sitting there, we can't use it, and it's still allocated to us, and if we did this enough times, we'd be at 8 gigs of memory again, and our programs will die. So, the function returns a pointer, and it's going to be called create bender. Now it needs to be able to take in some information. So what we're going to do when we create a bender in this case is we're going to give them the name, the element, and the amount of power they have. So I need that information. So I'm going to use a string for the name. Oh, sorry. I don't think I want to give that the same variable name because I don't like confusing myself like that. So I'm going to use input name, input element. So this way, when I'm using them inside this function, that I'm going to be able to tell them apart without accidentally saying, which name am I talking about? Am I talking about the new bender's name or the name inside the struct and stuff? So I would say input name, this is the stuff I was given. And then input power. How long's that line? Oh, yeah. 81 characters. I think I'll be okay with 81. I could very much, if I wanted to, split this into multiple lines, as I did in the slides, because I have less than 80 characters in the slides to be able to work with. But 81 I think I'll get away with here. You note that character arrays, when I'm specifying their length, I will specify their length. A pointer to a character, as we've seen, a pointer to a character is a memory address in the same way that an array is a memory address. So I'm actually using, and this is a very common standard in C, is to use char star, character star, as the pointer to be a string. Because we're saying, here I'll give you the first letter of the string, and then it's up to you to read until you find the null terminator. So we're not saying how long this is, because we don't exactly know how long this is going to be. Because a name or the input element is not always going to be max length. It's nearly always going to be shorter than max length. So I'm saying, don't worry about how big this thing is. Just read until you find the null terminator. So that's why a lot of the time with strings, we won't have the input specifying the hash defined how big it is or anything like that. Okay, so here's my function. It's going to return a pointer, and it's going to take in the information that it needs. And so I will create that down here. Create bender will allocate memory for a struct bender. It will populate the fields with the input information. It will return a pointer to the allocated memory. I want to be really clear about what's going on here, right? Jamie's asking, shouldn't it be a pointer to power? I'm not worried about this being a pointer or not, because I'm creating a new bender and I want the information to go into the new one. So these aren't even, these are kind of pointers, but not in terms of like, these are strings. And this is a value. So it's just a numerical value, and I'm not worried about whether it's something that comes out of my main or not when it gets there. It's just a value that I'm going to throw into the thing that I create. So you'll probably see as I build it. So first thing that I need to do is I need to do my memory allocation. So remembering what I'm doing with my memory allocation, I will always start with a pointer to the thing that I'm trying to allocate, and it's going to be of the type of the variable that I'm trying to allocate. So I'm allocating a struct bender. I know that because that was the whole plan for this function. So I'll need a pointer to that. I'm going to call it new bender, because this is the new one that's being created right now. So sometimes, you know, like I'll name my variables really carefully so that I don't confuse myself as I'm using them in the function. So I've got a pointer to a new bender. I know that when I call malloc, malloc is going to give me back a pointer to the memory that's allocated. So I'm storing the pointer there in new bender of what I've allocated. The other thing I need to do is I need to tell malloc, tell the memory allocator how much memory I need precisely. So if I want to, this is the dumb way to do this, but I want to show you. If I want to, I can say max length is 1024. So I can say 1024 multiplied by, how big is a character? 8 bits, 1 byte. Okay, so that's 1024. So I don't need to multiply it by the size. And I can add that to 1024, which is the number of characters there. And then this is an integer, which is 32 bytes, which is, 32 bits, which is 4 bytes. So if I wanted to, I could do something like this. What I'm going to tell you is to never do this, right? So I could think that I know exactly how big the struct bender is, and so I put in those numbers there, and I say, okay, this is exactly how big the struct bender is, so I will allocate memory of that size. I keep going on, working on my code and stuff, and I go, oh, I want more information than that. So I want these to be characters in a computer game, so I want them to have, like, their attacking power, but their ability to take damage as well. So I go, okay, they've got health. And that's cool, that's fine. I've changed the struct, and then later on I'll go and do things with it. However, this now doesn't work. And I would have to go back and change this. And so this is really fiddly. I don't like working with these kinds of magic numbers, especially when we have tools to work for us. So Sizeof is going to look here. At the time this runs, it's going to look at this and say, based on this definition, I will count how big this thing needs to be, and I'll tell malloc how big it needs to be. And now I will never need to change this. And I can do anything I want with this struct. I can add, remove things and stuff. This thing will always know the right size when it goes to allocate it. So then I'm free to make these changes without this thing getting confused. So Sizeof, super handy, does a lot of our work for us. Okay, so this is the bog standard malloc line. Malloc, size of a particular type. The result is a pointer to that same type. So the star means the pointer to this type. Size of here is how big that type is. Now I want to go in and change the fields inside it, because at the moment they've been allocated and they're just like empty pieces of memory. So seeing as they're empty pieces of memory, I want to fill them with the information that I need. So I'm going to say that the new bender. Now, how do I access the fields inside this? I have two options, the dot or the arrow. The dot is for accessing inside a variable. I don't actually have a variable. I only have a pointer. So I've got the pointer to a struct bender called new bender, and the only way to access the fields inside a pointer is to use the pointy way. So the arrow is pointy, so it accesses inside the pointer like that. And if I want to access the fields inside a struct, I need to know what they're called. There's the name, the element, and the power. So new bender's name, I want to set up as being the input name. However, I can't just smush strings into each other like that. So in order to copy a string into another string, I'm going to use the helper function from the string library here. And one of the helper functions in that string library is string copy. So copying into new bender.name from input name. That function will do the same kind of thing as me saying new bender.name is equal to input name, except this will make sure that all the characters are copied over. They will make sure that they read up until the null terminator, that kind of stuff. We'll do the same thing with the element. So the new bender that I've just created gets the element that was given to us in input. When we're doing this with the integers, we don't need to do anything weird like string copy. We can actually assign these directly. So the new bender's power is equal to the input power, which is just a value that we've been given. Okay, so now we have allocated memory. We've filled out the fields, and then we return the pointer new bender. I might actually just separate this into 3 paragraphs. So here's the memory allocation, here's editing the fields, and this is giving back the information. Okay, so now I can call the create bender function, which will allow me to make one individual for this team. So if I want to then set up my team, I would say I need to allocate the memory for one of the structs, and at this point it's going to be the team structure, give them a name, and then create some team members. So I've got 3 team members here, and I'm going to create them like that. So the first thing that I'm going to do is say create a pointer to a team. So what do I call that team? Oh, I just called it a bender team. That's fine. So I'm creating a struct. I'm creating a single variable, which is of type team, type struct team, basically, calling that bender team. And I'm going to memory allocate that. In order to memory allocate a struct team, I need to know how big a struct team is. So size of struct team. Again, you'll see this will be coming up again and again and again. Every time we allocate a struct, we'll have a pointer to the struct, and we'll have to have asked how big the struct is in our memory allocation. So get used to that line. We'll be seeing it a lot. In the same way that you might fill out the fields, this team has one field that we're going to want to fill out. The rest of them we'll see. because we may fill those out as we create things. So this is a string copy. The Bender team's name will become Avatars team. Note, interesting things that we can do. There's name in both of these, and that's fine because these are both underneath something else, some other variable type. In the same way that you can have two different arrays and you do element number 2 of both of those arrays. We can index into number 2 of both of those arrays, and we know that they're not the same variable. Each array has its own number 2. We can do the same thing with structs. Each struct has its own name, but we know that these are going to be separate strings in their own pieces of memory because we allocate memory for the Bender separately to how we allocate memory for the teams. We know they're in different places, so we know that even though they're called name, because they're accessed underneath the struct, they'll be separate and different. Okay, so let us create one member of the team. So we're going to say, we know that in the team, there's an array of pointers. So what I'm going to say is Bender team members. So this gets me to the array. And I'm going to say first element of the array. I'm assuming for the moment that team size has something greater than 0 so that I can do this. If we wanted to be more careful, we might check these things beforehand. But for the moment, purposes of this demo, I'm going to do this. So the struct team. Inside the struct team is an array of team members. Team members here. I'm going to go to the first element of that array, which means I'm down to the level of a struct Bender pointer, which is good because create Bender is going to give us a pointer to a struct Bender, which means I can now call create Bender here, and I can put its information in. So it's a name, an element, and a power. So I'm going to start off with ang. Name, element air. I'm just going to say air for the moment. No spoilers. No spoilers. And 10 power. Now that I've put one member in the team, I probably need to set up this team size, and I know that this is an uninitialized number because all I've done is allocated memory and I've only changed one variable. So since that's not allocated, I'm going to have to create it. Well, not create it, but initialize it. So Bender team number of members is equal to 1 now that I've put one member in. So this is me just tracking how many members are in the team. I will now do the same thing for the other characters. I'm just going to do this quickly. So I'm going to say Katara, and Katara's element is water, but we know that Aang is a bit more powerful than Katara, so we're going to give her 6. I can't remember what I did on the slides. I was having the same discussion with myself on the slides. Like, what's the power level between different Benders? This time I'm not going to set it to a number. I'm just going to do a ++, saying I've added a member to the team, so the number of team members goes up. I'm going to copy and paste this and do it again for another member of the team. And this is funny because it's not a Bender. So Sokka's not a Bender, which means no element, and Sokka, because he's the hilarious comic relief character, has a very low power. One could say that things do develop in different ways at different times. Yeah, Sean's like, yeah. Mark's throwing shade on all the other characters. Yeah, wait till I put Prince Zuko in. It's gonna have like power off the charts. Which is true, because he was kind of... I'm trying not to spoil it, so at the beginning, yeah, he's way more powerful than the others. Anyway, so now, at this point, we will have a team structure. And inside the array for the team structure, we've got pointers to each of these structures. So we actually have 4 things in memory now. We have one thing, which is the team. And the team has pointers to these other things. Wait. Much better, rather than me waving my hands around. Okay. There's the team. And this is Ang. Katara. Actually, Sokka can have the same color. And inside the team, there's an array of team members. Oh, there's only 3 elements in that array. And those are pointers that give us access to these other pieces of memory that have been allocated somewhere else. There's lots of different ways we can do this, right? Because sometimes, often when I'm doing this, I'll actually allocate all of these inside the team. So instead of this being an array of pointers, it'll actually be an array of the struct benders themselves, and that keeps all of my memory together. But I wanted to show you like this allocation thing. So each of these is allocated separately, and each one has a pointer to them. Okay, how much time do we have left? Not much. There's also ways to create the fields without using structs. So I could have a variable that is not a pointer, like so. Actually, I'm going to say of a struct variable. So I could just declare it in here like this. Struct bender Zuko, and then I can do the same kind of things with the fields. I'm gonna copy the layer. Oh, actually, no, that doesn't matter. So I could do string copy Zuko dot name. So because this is a variable, as opposed to a pointer, we use the dot. So Zuko's name is, let's give him his honorific title, Prince Zuko, etc. So I could do more stuff with this variable, and anything that I do with this variable would have the dot, as opposed to here, for example, where I have a pointer to a bender, then everything I do is with the arrow. So accessing the struct fields is a little bit different like that. Oh, Miguel's like, why aren't I using CS Paint to draw my diagrams? I was wondering, how did that whole discussion end up there about boundaries and stuff like that? And like, no, the lecture would get really, really long if I did that. Okay, so if we wanted to, we could print out the contents of the team, because at the moment, we have a program that I'm building up that we haven't used at all. And because I'm running out of time, I'm just going to copy this. Because I think in terms of like looping out to print something out, you've probably got a decent idea of what that is already. So I'm going to copy this and put it in my functions section up here. So, cool thing that I'm doing here. Printing out the team involves only taking in one struct pointer. Because I have the team and I have the pointers to all the other things, I can access all of these pieces of memory just with access to the team. So what I'm doing here with this printout is print out the team name, so whatever that was, and I think we set it up here as the avatar's team, and then we loop through until we hit the number of members in the team, and then we print out the name and the element of each team member there. So we're not actually printing out the power of them here. Maybe the power is some like internal statistic that we're using in a game or something like that, but the things that we worry about are the name and the element. So this is just looping through and printing that out. Let's at least see that working. Well, we'll see if this compiles first. Ah. I mean, I was working pretty closely with my slides, which was written... The slides are written from code that I know compiles. So let's run this. Oh, I was like, why don't we see anything? It's like, I made the function, I never called it. Okay, so we can print out the team here. Print team, vendor team. Compile this and run it. Okay, so team name is the avatar's team. Ang uses air, Katara uses water, Sucker uses none. Take that, Sucker. He's actually my favorite character, but I also like to make fun of him. I make fun of my favorites. So what we have here is the kind of thing where we have structures for custom variables. And custom variables, you can see, makes so much sense when we're looking at a character and all the different possible statistics that we could have for a character. We can bundle them in one variable, and then we can access those bits of this variable using these arrows and things. Let's just, for a moment, compile this with leak check. Because as you notice, I have not freed anything yet. If I run this now, leak check is going to say error. Free not called for memory allocated with malloc in function main in benders.c at line 31. Leak check is nice to us. Leak check gives us a lot of information. So line 31. The bender team. So one of my memory allocations here has not been freed. I know that in create bender, there's another memory allocation, so I would probably have to free all of that memory as well. I'm out of time, so I won't get to show you the code for that, but don't worry, on Friday... Oh, actually, I don't think we're even freeing memory on Friday. Well, when we get down to it, we're going to have some complex structures and we'll free them, and I'll show you freeing code. Having said that, there is some information here if you want to. So I copied in the command that I used. I used leak check with a hyphen here. They both work. They both do the same thing. And it shows that there's memory that we're missing, and there's some code here for freeing the memory. So what we can do is we can get the pointer to the team we're going to free, and then we free all the members that are in the team, depending on how many members are in the team. And then after that, we free the team itself, and that's going to go through our memory and say, I will first go through the team members, and I will free up this memory, then this memory, then this memory. So that's the loop here that loops through and calls free on each of the pointers to team members. And then after that, we'll free the team itself. So we have to do it in this order, because if we freed the team first, then we wouldn't have access to the pointers to the team members anymore, and that would cause a memory leak. So after we've freed everything inside it, then we free the team itself, we've freed up all our memory, and we're happy to continue. Okay, so that's it for today. Today we have learnt a bunch of new stuff about how to handle memory. So 2 important things. One, we've learnt how to create variables that persist beyond the function they're in. So they persist even beyond the curly brackets that they're in. So what goes on inside the curly brackets stays inside the curly brackets is a rule that we're using for all of our normal variables. We now have a way around that if we want to. So we can create things in a function like this that last longer than their function. So up until now, if you had to create something in a function, it would have been weird, because anything you created in a function would have disappeared. But now we have a way of making something in a function that lasts longer, which means our creation of things can be kind of pushed out into functions, which makes this much cleaner and neater. The other thing that we have done is we have learnt about structs. So we've learnt about creating our custom variables that have lots of little bits inside them made up of other variables, even to the point where we've shown that we can use structs within structs. We didn't really use structs here. We only use struct pointers here. But if we wanted to, we could, just like that, have put all of the memory for each of the individual benders inside the struct for the team. That would have made this whole demo much less complicated, but also would have meant I would have shown you less code about doing stuff like the creating the benders and things like that. I'll put some comments in here about that before I upload it. Okay, so we're going to wrap it up there. We'll go on break for a bit to say that official lecture is over. I'll come back afterwards, answer any questions you have. I'm sure there's going to be questions because this has been a very, very technical lecture where I'm showing some new techniques. So stick around if you want more details. Back in a moment. Alright, I'm back. In that like 1 or 2 minutes that I paused there for a second, I was like, how do I rhyme with Avatar? I was like, make up a rap. Come back with a rap about Avatar. And then I was like, okay, that didn't happen. the closest I got was like a song where someone completely mispronounces a word to rhyme with something. It was like a song where someone goes something rah rah rah, I'm gonna shake it like a Polaroid, and I was like, that's not how you say Polaroid. But anyway, that was the closest I got, and I couldn't really figure out how shake it like a Polaroid had anything to do with Avatar, so I'm just gonna stick to what I actually know how to do and talk about programming. So did we have any questions people had about things? I can assume there are probably going to be some, so I will wait for a moment and see if anyone has any questions about this setup. I mean, don't worry too much. A lot of your questions will be answered in next week's tutorial and lab, but if anyone's got any now, I'm happy to answer them. Hopefully things are sinking in a bit. I mean, you can kind of see from what I'm teaching right now that we're kind of finishing off the stuff that we've done in whatchamacallit, in assignment 1, like all the C code with arrays and stuff like that, and now we're branching out into this new idea of like, how do we grab pieces of memory and how do we do custom variables, and we're going to be using this stuff on Friday to make a new type of collection of variables. Okay, so Stefan's asking, can we explain how the code is run again, like the order of code? This is a really good question because we're no longer in the realm that we're in before. You know, when things were simple, Kat was laughing about when things used to be simple and we were printing out smiley faces. I love that was only 2 months ago. One of the things I love about 1511 is being able to take people from not being able to code at all into actually being quite seriously capable of coding. I think it's really cool. A lot of people think that they aren't. But when we get to the end of week 10, if I was to say to you, go back and do like weeks 1 to 3 without any help, you'd just be like, yeah, I can just do that. I can do that without even worrying about how this stuff works. Osama, I still don't understand the point of pointers, and totally get that. There are ways to program without ever using pointers. If your programming language is set up in a certain way, you will never need to address the memory of other things, and so there are other languages that are set up to never have to use it. C does it this specific way because there's a lot of stuff that we can do if we're accessing memory directly. There's a lot of stuff we can do to actually organize things that work really well. But anyway, let me go to Stefan's question here, which I think is really interesting, because we've got all this stuff, right? This and this are not running code. You know, these never run. They're things that are reference information for other parts of the code. So in order for this to run, these things have to be set up in advance. So we have to know what these things are, and we have to know that these functions exist so that we can jump to these functions later if we need to. So the first thing we do, vendor team, memory allocate, Sizeof, struct team. So malloc jumps into the C standard library and runs a function there. I wonder if we should do this visually. Oh, there's too much to try to draw here. I don't know if you saw my eyes roll back in my head just for a second there as I was thinking about what I was actually even going to draw. But let's try. Always should at least try. Oh wait, save. I don't need to save that. New. Don't save. Okay, so the malloc, I was just like, okay, so the main, and then we go into malloc. And when we go into malloc, a piece of memory gets created. And it's a team-sized piece of memory. Malloc then returns to the main. The main doesn't just have this team-sized block of memory, so let's say the main's memory is this one. The main now has, what's it called? Vendor team. I'm just going to call them B team, because I'm writing words with my mouse, and that's not great. Okay, so after the malloc, we have the vendor team here, and that's the team. Then what we do is we string copy into there. So string copy, I actually won't do this one, because I don't think this is as interesting as the other functions later. This is going to go into the string library, and it's going to copy some information into the vendor team. But I think it's more interesting to look at this. So what we're going to do here is we're going to create vendor. So the first thing that actually happens in this line is the create vendor function, because this is an assignment to a variable. And if it's an assignment to a variable, we have to resolve what's being assigned to that variable first. So create vendor gets called. Oops. Go back to black. Create vendor. So it actually gets its own little piece of memory here temporarily. I'm just going to call that create, because I don't have to keep typing this stuff in. Okay, so create vendor runs. And when create vendor runs, we jump down here into the code, and it says allocate memory for a new vendor. So create vendor allocates memory. It has new, newbie, because it's new vendor, noob, points at this one. This is a vendor. My mouse handwriting has actually gotten better because of this subject. I used to have a tablet. I used to have a whole tablet laptop that I would use while I was lecturing. But since I've been working at home, I haven't been using that laptop, and it's just more convenient for me to just use this one. Anyway, so we've created this new thing, and we fill it out with details. Let's just assume that these details are correct. Then, when create vendor returns to the main gets given a pointer to this vendor. But the pointer that it was given, so here we would return a pointer to the new vendor after filling it out, which means that the main now owns a pointer to this. When the create returns, it automatically gets scrubbed from our memory. So now the main has a pointer to the bender, but what the main was doing with that was here. After it had run this and got its pointer, it was assigning this to the first element of the team members array inside the bender team. So the bender team here has an array. Happens to have 3 elements, and the main says this pointer is here. So that pointer points at bender. The main doesn't keep a copy of this, so let's just let that go. Like so. So by the end of the first create bender function, the team here, team member 0, is set up as the result of create bender, and the result of create bender is a pointer to the memory that was allocated, because we return this same variable here. So after we've created our first bender, the create function, which is now gone because it finished, allocated this memory. The team's first element is a pointer to that piece of memory. Hopefully this is helping, because this is the kind of like if we see how this is working, what we had before previously was all our memory is in the main and all of our stuff is in the main, but now we can create these pieces of memory that are outside. They last longer than the functions that created them and things, and we track where everything is by our pointers. So the pointer to the team, the bender team there, the bender team has pointers to these other things, and so we can keep track of everything we're doing by knowing where everything is in memory. So our pointers, I guess, Osama, as we were talking here, that the point of pointers is really to say that we now have control over large chunks of memory, and our pointers are our way of just marking where things are and remembering where things are. Okay, so Stefan, I hope that's helping a little bit. So this was me stepping through the order and showing which things are running when. And you can see how we're jumping around in and out of functions and stuff like that. Even though we are still going line by line through the main, every time we call a function, we're going to go and run that function and then come back. That function is going to give us some information. It may create stuff in memory. It may remove stuff in memory. It may loop through things and stuff. But the way that we're always going is line by line through the main. But every time we call a function, we jump to the function, we go line by line through the function, then we go back to our main. Or we call another function inside that function, we go there, and then we come back. You know, so there's this flow that we'll always be following through these things. Ningting Jiang's asking, should we remember each variable type size for the exam? Not necessarily. Remember that the exam for COMP1511 this term at least is an online open book exam. So it being an open book means you can look up my lecture slides for how big each variable is. Or if you really want to, because you've got time to do this in a longer exam, well, actually you could just do this anytime you want to, is Sizeof struct team will actually give you a number. So this is actually like malloc takes in an integer. So Sizeof struct team will actually be an integer. Like let me show you something. Printf team is this many bytes. Sizeof struct team. I'm hedging and guessing this will work. I'm pretty sure this will work. So this is actually going to tell us this. So I'm going to DCC that and see if that works. I think this will still work. Format specifies int, argument has a type unsigned long, which is a type of integer. Let's see if it works. Team is 1056 bytes. So if we look at team, maximum length there is 1024, and then there's an integer which is 4 bytes, and then a struct bender pointer which is should be a 64-bit integer, so it should be 8 bytes, so 1024 plus 12. There's something else going on here. I'm not sure exactly what it is or why it's 1056 bytes, but the memory allocation would be 1056 bytes for the team. So obviously there's something going on here about how I'm adding these things up. Oh no, this is an array. This is an array of pointers. So it's 8 by 3 is 24 bytes here, and 4 bytes here, so it's 28 bytes plus 1024. 1024 plus 28? I don't even know if I'm adding this right. I'm just kind of rushing through. But either way, Sizeof struct will actually tell you how big something is. We could do other things. We could even do just like, what's the size of an int? Or what's the size of a double and stuff. So you actually have all the tools in your code to actually understand how big a variable is without having to look it up. So you don't even have to look it up or memorize it, because Sizeof is actually going to count for you how big something is. And also the fact that I'm getting confused about how we got 1056 is another reason why we should never put numbers in here. Because the human has a chance of getting it wrong. Like, I'm still confused as to why exactly that is, and I'd have to go back and look at it. Whereas, why would I bother when I know that the computer can do it for me? Guru-chan has an answer for Osama that you can't do scanf without pointers. So scanf says, take in some information and write it into a memory address. In which case, one must need a memory address to be able to do it. So, yes, and I think that, but there may be other ways to do scanf. We could do like an fgets or something instead, but scanf is more powerful than fgets in certain ways. Like, you can get something and read in characters and treat them as a number and all this kind of stuff. So there's a lot of little bits and pieces that pointers can make things very, very easy to do. They do make thinking about code more difficult, because you have to not just think about that you have values that you've stored in memory, but you have other things you've stored in memory that are the addresses of those pieces of memory. So you have this second level of looking at memory. I like them because of the potential for doing cool stuff with them. So they have some capabilities that just normal variables don't have. So we can do interesting things, like I can have pointers to these team members, and I can swap someone in and out of the team by, say, having a, let's say, struct bender pointer reserve bench. And I could say that reserve bench is equal to, let's say I put, I'm going to put sucker in the reserve bench. I put sucker in the reserve bench. So what I'm saying is I now have a pointer to him there, which means this memory still exists. But then what I can do is I can say bender team members 2 is equal to create bender, slight spoiler here, which is going to be like an 8. I don't think anyone's as powerful as AIM, but it's definitely very, very powerful. So what I can do is I can bench whoever is in that slot, and then put someone else in that slot, but I haven't lost the bender that I created here because I've got a pointer to them on the reserve bench. So what I'm doing here is like, let's get another color. So if I did something like this, I go, here's my reserve. saves that location, and then this thing could then point off here at another newly created bender. I mean, like, I'm just squeezing things in here. And so we can start doing all this cool stuff with pointers, where we're like, I'm not losing any of my memory, but I'm changing what things mean by what labels I'm connecting to them with pointers and stuff. Yeah. So there's some interesting stuff there. Okay. Dan's asking you if I'm uploading the code to WebCMS. I will be uploading the code to WebCMS once we're done here. I'm wondering, because I actually have this same code that I prepared earlier with lots more comments in it, so I may actually give you a version that has a bit more information that's talking about what's going on. I take some of this stuff out, though, because I don't want to confuse matters by leaving too much random code in there. Zeal's asking, why is there a star in front of the function name when I declare it? What is it good for? Okay. Here. Very important. The star is not attached to the function. The star is attached to the type. So it's always the thing on the left. Well, sort of. Like, it's attached to both. There are subtleties as to why it's on the thing on the right, but I'll show you that in a second. But anyway, this means that the function's output, the function's type, is a bender pointer. It is not a struct bender function. It is struct bender pointer function. So when we create a pointer to a bender here called new bender is of type struct bender pointer, that is the thing that we're going to return. And it's important because we're not giving back a struct. This function's not giving back a struct, it's giving back the address of a struct because it created one somewhere in memory with a memory allocation, like so. Let me just get something bigger so you can see where my pointer is. Like so. And then when it gave the function, when it gave the information back to the main, it did not give this struct back to the main. It gave this pointer back to the main so you could access that struct. So we said, we set up this thing in memory. Here is the location of the thing that we set up. You can store that location wherever you want. So we stored that in the team. And the team, this here, so if we were to look at this in great detail, this memory location here would be like 0x6fc. I'm just making up stuff there, right? So that is the address of this piece of memory, which means what gets written here is not just the end of this arrow. In here, oh, you're testing me here. 0x6. Oh, look at my precision and control. Right. That value that gets written into that array is the address of this piece of memory here. So I draw these things as pointers, as arrows and stuff like that. But what's really being stored is where this thing is. So this thing exists at this location in memory. We write that location in memory into this array so that we can access it again. Girichan said, wait, am I... Okay. Girichan said, you used Sizeof without brackets. Why is that possible? It is not. I forgot. And I'm going to go back and change that, actually. Because I think that was me fiddling around with things that I shouldn't have been. I actually changed that during the talk, didn't I? Okay. Sizeof wants everything. Fix up my colors. Yeah, Sizeof wants everything in brackets. So it wants to be really, really clear that the type that you have in there is one type. So that way we can do things like later on, where are we? Here, it knows exactly how many words it's reading because it reads what's inside the brackets afterwards. So that was my mistake because I did that like while we were talking. I was like, oh, this doesn't need the brackets. So I forgot that it actually did. On instinct, I put brackets in all the time, but I wasn't sure if it needed them. Okay. Stefan, what do we do for the final exam? I will talk about the final exam later. The final exam will be very similar to something like a lab. It's longer and harder than a lab, but it will be questions like that. There will be some questions which are more thinking about tutorial style questions where they're like, if you know this, you know what to say here. So they're testing whether you understand sort of techniques and things like that. But the majority of the marks in the exam is, I need code that does this. Please write the code that does this, and then you'll have to go through and solve the problem. And the difficulty scales from, first question in a lab through to challenge question. So again, similarly to the stages in the assignment, they'll go from easy to hard, and there's a point where you stop. So there's a point where everyone in the course will reach a point in the exam where they stop and go, this is as much as I know, and I hand it in at that point. You don't need to do a stupendous amount in the exam to get the marks that you need to pass the course. Everything above the marks you need to pass the course is just like us being able to assess what extra knowledge you picked up along the way. I will go through, I have an entire lecture that details what's in the exam. There is a lecture that you can, even on YouTube, you can see, which is last term's exam. I don't 100% suggest watching that because it's not the same, but if you want to, you can get an idea about how I assessed this subject last term. We're in a weird flux state where in previous terms I would be able to say to you, just watch it, and it will give you useful information. But while we're in this weird online teaching world, slowly transitioning back into face-to-face teaching, things are still in flux. So some stuff that I say about the exam in the previous terms lectures is not going to be the same. So you can watch it for an idea, but don't take it as the truth because it's for last term, not this term. Zeal, it's not going to be a 24-hour exam this time. It's going to be a little bit shorter than that. But we won't go into explicit details until I have written exactly what's in the exam and I know what's going to happen. Like, I don't really want to talk about it because I haven't finished it yet. So it's kind of like if you ask exactly what the format for assignment 2 is, considering that's coming out on Sunday, I do have more information about, like, I know that there's 5 or 6 stages. I can't remember. I think it's the same number of stages as assignment 1, but I can't remember whether we were splitting one or not. See, we haven't even finalized that, so I don't want to tell you exactly what's going to be in the exam when I haven't written it yet. But I can give you a lot of vague ideas. I mean, the plan, I've got a plan, I just haven't filled it out completely. Yeah. And Zeal saying, thanks, got it, because it returns a point. Yes, there you go. And Stefan saying, needs to be done in a shorter amount of time. Yes, the exam will always be shorter than the labs. We're not doing a week-long exam. And also the labs are there not just for you to do, but also for you to talk about people with and share your code with other people, and so that you can learn how other people are doing things, work with other people, do code reviews amongst yourselves if you want to, that kind of thing. So labs are designed as a, if you want to, a partially collaborative thing. Whereas the exam's obviously not collaborative at all. Again, this is difficult because we're in this weird online world where, like, I'm not gonna come around to your house and turn off all of your internet connected devices and get you to do the exam. That's a weird thing to do in this online world. So it's mostly that we're trusting you to work on your own, and when you don't work on your own, we kind of know. Like, your code looks suspiciously like someone else's, and we're like, don't do that. Doesn't help you, Trent saying decimal spiral level. There will be a question at roughly that difficulty level at the end of the exam. So if you reach that question in the exam, you kind of know already where you're up to. So even, like, I've seen people, like, I don't want to get too deep into how the exams work, but in the past, I have people who I know got HDs in the course, so the highest bracket of marks in the course without attempting the final question in the exam. So that's the kind of difficulty level that the final question in the exam will be. Yeah, so we'll get there. We'll talk about this later, though. Like, I literally have an entire lecture on the exam and how to prepare for it and what to do in it and stuff like that. So we'll get there at the end of the term. But we're still in week 7. We still have content to learn rather than thinking about how we're going to be assessed on content we don't even know yet. All right. I think I've covered everyone's questions. I've caught up with what's in the chat. We got a bit derailed by exam talk, but I think I don't want to. I'm not gonna say I'm not gonna tell you anything. But if I have stuff I haven't finalized, I'm always gonna tell you that this isn't done yet. But we'll get there. All right, I'm gonna wrap it up there. Thank you everyone for coming along. Thanks for sticking around and asking questions, because there's a lot of interesting stuff that we talked about there. I will upload this code later on this afternoon. It depends on, gonna grab some lunch first, but then I will spend some time cleaning it up and putting some comments in so it's really clear what's going on, and then I'll upload it for you. Okay, see you soon.